Hello again. Welcome back. So today we're gonna slow down, I suppose. The last set of videos have been maybe intensive. Uh, it's kind of optional, right? I've been doing proofs of statements, and it's up to you really if you wanna see the explanation to these statements or if you just wanna accept them as truth, right? Like I said, I think it's a good idea to challenge yourself. But today we're gonna be doing something easy. Instead, I'm just gonna be expanding on sets, I suppose, um, giving more examples of what they are. Well, actually, exploring some cool properties about sets. So truth be told, these prologue videos, in order for everyone to be on the same page, right? We're almost there. I really wanted to go over axioms, but I really couldn't go over axioms without going over sets. Well, just because axioms of the real numbers. It's kind of cool to see the set of real numbers show up over and over. Well, I guess it's supposed to, right? Because we're dealing with numbers. But nonetheless, that cool mathematical language. Without set theory or without sets, I there's no need for it, right? So yeah, I wanted to include sets, and it just so happens that I had to show you guys this mathematical language. But yeah, right. So knowing what the axioms of real numbers are was definitely something that should put everyone in the same boat because it gives you 10 or 11 axioms of, these are factual mathematical statements that you can do when you do algebra or something else, right? I suppose that I also give you four more, but about the inequality signs, like less than, greater than, right? So 15 axioms, but more than that, right? You can use those 15 axioms to create even more true statements, so that you know what you can and can't do in a math class, in an algebra class, whatever. Well, I suppose that in order to prove that you can do something, you should do some type of formal proof to disprove that you cannot do something specifically. Well, the thing about proving is that, yeah, to prove something, you do need a formal proof. But to disprove something, all you need is one counterexample. That's why, mathematicians, they do the whole thing about like a statement is only true if it's always true, right? Meaning that if it fails once, then it's not a true statement. So if you ever in the algebra class you do something and you're like, is that legit to do? Well, try it out with numbers. Try it out with like plugging in actual numbers into the variables, and did it work out? Well, maybe you could have gotten lucky. Pick maybe a couple, do it a couple times, and if you get that one time it didn't work out when you actually plug in numbers, then that thing that you think is legit is not legit, right? But okay, right? So in order for everyone to be in the same level, supposedly, we're almost there. In the same way that I wanted to go over sets before going all over the axiom stuff, right? I want to go over exponents because that's very important in algebra. Like how do you deal with exponents? But before I talk about exponents, I want to talk about functions. It's weird. It's because I really want to look at one specific type of function. And before I look at functions, I want to go over sets a little bit more. Well, in particular, there's one set that you have to, I think, talk about when you talk about functions. I mean, okay, not really, right? All your high school teachers, they talk about functions and they don't really show you this one specific uh, set. But this set comes out of two sets. So what I mean by that? Well, the thing is that on the first video, I only kind of introduced what a set is, right? And I gave a couple examples. And I said, the sets are interesting, right? Well, one thing that makes them interesting is that you can apply a binary operation on sets. You might be wondering what a binary operation is, but you actually seen them. Actually, you've seen them a lot. Even in my videos, you already seen them. For example, addition, right? You add two numbers and then you get a third number, right? Addition is only something you can do two at a time, right? Like if you have 3 plus 5 plus 7, well, you gotta either add the 3 plus the 5 or you gotta add the 5 plus the 7 first, and then whatever you get, then you add it again, right? That's why it's binary, right? So addition is binary because you need two to give you a third new number, right? Well, yeah, addition, multiplication, subtraction, and division, they're all binary operations, right? Well, the thing is, when you have sets, not that you can, well, you can add sets. If you have a set A and a set B, you can have a, what does A plus B mean? However, um, it don't something like that becomes more meaningful way in the future. Instead, right from the get go, right at the level that we are right now, there are binary operations that, again, if you've already taken an algebra class, you have seen. You just didn't see them as binary operations. So yeah, in this video we're not gonna prove anything, which I don't know if that makes it less boring or more boring. I'm just gonna show you what these binary operations on sets are, and let me know what you think about. Do you prefer? I would like to know for real. Do you prefer proving? Do you prefer when I do a video where it shows proofs, or do you prefer where I just kind of show you this idea in mathematics? Let me know. Okay, let's get into it, right? So, binary operations on sets. So, we're gonna look at the binary operations of sets. Well, because again, right? What's a binary operation? Well, like I said, I already said addition, subtraction, multiplication, and division are binary operations. What does that mean? It means that if you have if you have two numbers and you apply a binary operation to it, then you might get a third number, right? 6 plus 3 will be 9. 6 minus 3 will be 3. Okay, we didn't actually get a different number, but that's fine too. 6 times 3 will be 18. 6 divided by 3 will be 2, right? So again, so what's a binary operation on a set gonna do? Well, so hopefully it means that we have two sets, and then applying a binary operation to it gives you a whole new other set, right? Possibly. Now, in very me fashion, before I actually get to the binary operation sets, I want to give you something that's kind of long overdue, but I do want to talk about. So what's a subset? I never really defined what a subset is, right? Subset. So, so we say, for example, that A is a subset of X if and only if. So if I put IFF, that just doesn't mean if, it means if and only if. For every element in A, that element is also in X, meaning all the elements in A have to also be in X. That's what it means to say that this is a subset of that, this is a subset of that, if every element here is also in here. So that's what a subset is, right? If we draw pictures, maybe as a Venn diagram, you could say, right? You could say that, let's say that this whole thing is X, and that A is right here, right? And what I'm trying to say is that all of A, right, if these are the objects inside A, then they're also inside of X. That's what it means to be a subset. So let me give you a little example of what isn't a subset, right? Suppose that A is 0, 1, 2, 3, and 4. And then suppose that B is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, right? So can you say that right, is a subset of B? Question mark, right? So is it true that every single element in A is in B? Well, 4 is in there, 3 is in there, 2 is in there, 1 is in there, but 0 is not in here, right? The fact that, that it's almost a subset, but it's not a subset. So it's actually A is not, you put a line through it, a subset of B. Yeah, almost being a subset is still not a subset. So yeah, we have to be very careful when if you tell me that something's a subset, it's because you're guaranteeing me that every single thing in it is in the other set as well. So even if it's only off by 1, we still say no, it's not a subset, right? Maybe picture wise, right? Maybe B is over here, and B almost takes up all of A, but not quite, right? The fact that there's like pieces missing means that no, you cannot call A a subset, even though it almost is a subset, right? So yeah, I gave you an example of something that's not a subset, right? Well, because I kind of, in the first video, so this is me really kind of trying to vindicate my first video. Well, because I'm expanding more on sets. By the way, that first video, I just wanted to introduce to you what a set is, which is really, again, a collection of objects. Definable objects, meaning just don't create a paradox. As long as you don't create a paradox, we'll be fine. Be cool, all right? But yeah, so I ended that video with this, right? The natural numbers. And I said, oh, every natural number is also an integer, right? It's meaning the natural numbers are a subset of the integers. And then I said, well, I made a case about how you can think that every integer is also a rational number. If you remember what the definition of a rational number is, it applies. And then, of course, if you're a rational number, then you gotta be a real number. Because, yeah, you can fit any rational number into a number line. Okay? And then the most interesting part was that I said this thing, complex number, right? Imaginary, but not quite just imaginary numbers. Well, again, right? Funny thing, real numbers are subset of the complex. Because again, every single number here is also a number in here. And it doesn't really stop there. It actually keeps going, but I'm not going to reveal what goes after, right? Not yet. There's no point in doing. But yeah, so again, you can think of all of these as examples of subsets, right? That's why, but it's also important to note what isn't a subset, A little more to just kind of redeem that first video. So I said something like this, for example. I think it was a set D, which I defined to be x's such that x squared plus 1, right? And then, like I said, it's important to kind of work with this more. Don't just leave it like that, because it could be ambiguous, right? So maybe one thing you could do that I couldn't do at the moment because I introduced, for example, the set of real numbers I introduced way at the end. Well, now you can say, okay, x's that are real numbers such that x squared plus 1 equals 0. Right? But it turns out that there's no such real number, so this also ended up being a set without any elements, which is we call the empty set, right? However, let's call this a D prime, and let's say you would have said x's that are complex numbers such that x squared plus 1 equals 0. Well, at that point, you're no longer empty. So there's actually this element called I. Again, if you don't want to call it a number, then call it an element. But this element I had the power such that I squared equals -1, so -1 plus 1 would be 0, right? But then also negative I would also fit that description, right? So see, being more descriptive of what kind of thing you're talking about changes the whole thing. Well, just to be more clear, right? Over here, as soon as I say I'm only considering real numbers such that blah blah blah, at that point you're implying that this D is a subset of the real numbers. Whereas over here, when I imply, okay, I'm talking about complex numbers such that blah blah blah, at that point I'm implying that D prime is a subset of the complex numbers. So that's one interesting thing to note if you see something like that, right? All right. So now you know what a subset is, and you know, I just didn't. Even though we're talking about binary operations, there was a reason why I'm bringing it up. Okay, so let's actually talk about binary operations, right? The first binary operation I want to talk about is the following. Let A and B be subsets of some bigger set X. I mean, you can from here on you can just think of this capital X as real numbers if you really want to. But suppose that you have two subsets of some bigger set, right? Then we're gonna define A union B. So this U thing is not really a U, but this U looking thing means union, and it's gonna mean the following set. It's gonna be X's in X such that X is in A or X is in B. Okay. Let me show you an example. Suppose that, let's say you have the set E, and the set E is just 1, 2, 3, 4. And then suppose that the set F is the set 3, 4, 5, 6, 7. I don't know, right? Well, then the set E union F is gonna be all the elements that are either in A or in B. I mean, all the elements that are gonna be either in here or in here. So, for example, 1 is in here, right? Because it's as long as you're in at least one of them, you're gonna be in the union. 2 is in E, so 2 has to be in the union. 3 actually happens to be in both of them, but like I said, you only needed to be there once to write it. So I'm just gonna write the number 3 once. Like I'm not gonna write 2 3s. What else is in the union? Well, 4 happens to also be in both of them. As long as it's only there once, I'm good. So then 5, 6, and 7. Right, so this set has 4 elements. This set has 5 elements. The union ended up having 1, 2, 3, 4, 5, 6, 7 elements. Okay. And let's just sets do go hand in hand with Venn diagrams, I suppose. So if I write a Venn diagram, suppose this is A, and suppose this is B, and of course the bigger thing is X, right? So then the union will be again kind of both of them, right? Okay, I don't want to overshade because I actually want to make the point that this middle part that they, like I said, in the same thing that I do not put a 3 or a 4 twice, it's just 1 3 and 1 4. You know, I don't want to double shade the middle. You don't double shade the middle. So the union is just that, everything that's shaded in blue, right? So yeah, right. We had one set, we had another set. We applied a binary operation to it, and now we came up with a different set, right? Okay, let's talk about another one. Let A B be a subset of X. Then now the other way around, A intersection B. So now this upside down capital U means intersection. So it's going to be all the X's in X such that X is in A and X is in B. So let's stay with the same thing. Suppose that E is 1 2 3 4. F is 3 4 5 6 7. So then E intersection F is again only the elements only the x's, only the elements that are in both a and b. So for example, 1 is not in there because 1's not in f. 2 is in e, but 2 is not in f. 3 is in both e and f, so 3 is definitely in the intersection. 4 is in both e and f, so 4 is in the intersection. And then 5 is not in both of them, 6 is not in both of them, 7 is not in both of them, right? So E intersection F now only has 2 elements, because these are the only 2 elements that they share, right? Let's do a quick Venn diagram. So if this is A, and this is B, and the whole thing is X, right? So then the intersection is again just what they share. So now this part that before I was cautious to not double shade, now when it comes to the intersection, that alone is the intersection. Just to clarify a little bit, why am I being so... This part even necessary, by the way, both in the union and in the intersection? You can make the argument that it's really not, but let me show you this example, right? So if we go back to this way, right? So, and let's say I draw some type of Venn diagram for that, right? Alright, let's see. What can I really draw this so that looks really good? Alright, whatever, right? So here's the natural numbers, and then it's a whole subset of the integers. Sorry, too big. Which is already a subset of the rationals, which is a subset of the reals, right? Well, let's keep going, right? The reals are in itself a subset of the complex numbers, right? So what am I getting at? What I'm getting at is there's this one very interesting set that it might catch you off guard. There's a thing called the algebraic numbers. Of course, math people can't stop, right? They gotta find new types of cool sets that they want to study, right? So what's an algebraic number? Well, we haven't really talked about a polynomial list, but an algebraic number is just any number that happens to be a solution to a polynomial. Right now, like I said, we're building math from the ground up, which means that what I just said to you must mean nothing. But in case that you do have some math background, right? So that's what it is. An algebraic number is any number that happens to be a solution to a polynomial. I mean, what's a polynomial? We'll get to that in the future. Well, if I wanted to write the set of algebraic numbers, well, it turns out that for sure every rational number is algebraic, right? So this is the naturals, integers, rationals, right? I should have done these with different colors. So I'm saying that for sure the algebraic numbers, which I'm drawing in blue, they for sure contain all of the rational numbers. But then they also contain irrational numbers. So this is a set that kind of again contains all the rationals, but then has some irrationals, right? Well, here's the thing. It doesn't just stop there. It also contains, and this picture is already kind of misleading, but it's also going to contain complex numbers as well. Again, this if you think, oh, this is the area of complex numbers that are out of all the complex numbers that are algebraic, again, it's not to scale, right? But then the funny thing is that again, you can very well make a case that this set even goes outside of the complex numbers. So like I said, let me do this one in red, right? If I'm putting this as a mystery. What's even up top of the complex numbers, right? Well, there's definitely something that's on top of the complex numbers, right? And apparently these algebraic numbers still kind of go over the complex. Well, I did this kind of on purpose. Who's to say? I mean, if this set, which again, algebraic numbers, right? This set already spilled out of the reals. And honestly, you can definitely make a case of why it also spills out of the complex numbers. Well, even if I tell you there's still this mystery set, right? Who's to say that this set of algebraic numbers doesn't continue to spill out, right? So just to make it even more weirder, right? I'm saying that the complex numbers might be a subset of something, but again, who's to say that it ends there? How do you know that this is not a subset of even something weirder, right? So what am I saying with this algebraic numbers? That if you just define a set that says, let, I don't know, let G be a real number that is algebraic. X is algebraic, right? This set will be a completely different set now if you say G prime, which is complex numbers that are algebraic, is algebraic, right? Which might now be a completely different set to X is in mystery set, so that X is still algebraic, right? So yeah, so the reason why, again, why did I make sure to include like this thing and that thing? It's just to say that my picture might not even make sense, right? If I don't make sure that I'm grounding them to, I'm only looking at x's of a specific type, right? Because again, this set of algebraic numbers seems to really be ever expanding depending on what numbers you're looking at, right? So yeah, this set, and that set, even though they're all saying, oh, as long as X is algebraic, well, depending on where you're kind of grounding them, then they look a different way. Again, same idea with the D and the D prime. Okay, well, actually, one more video, one more set. I mean, this is the last set we're gonna look at, and I'm glad that I'm making good time. All right, there's still one. Again, I want to talk about functions, so there's still one more binary operation on sets that I want to talk about, right? This time, this is the one time that maybe I don't even have to specify that A and B are subsets of X. This time, I really don't feel like I need to. But let's say that A and B are some subsets of set X. Then we're gonna create this whole new set called the Cartesian product. A cross B is gonna be all the coordinates little a, little b, such that so long as that the first coordinate belongs in the set A and the second coordinate belongs in the second set. Okay, so yeah, if you have some set A and some set B, you can create this whole new set, the Cartesian product of those two sets, to just be coordinates, right? Well, I keep using the set E and F, right? If E was what again? 1, 2, 3, 4, and F is 3, 4, 5, 6, 7, right? Then what's going to be the Cartesian product? Well, I'm saying it's going to be all types of coordinates, right? Any coordinate you can make, as long as the first coordinate is one of this and the second coordinate is one of those, right? Well, so because this only has 4 elements, this only has 5 elements, we can make a list. I mean, you could have a coordinate that it's 1, 3. You could have a 1, 4, a 1, 5, a 1, 6, and a 1, 7, right? So I think so far I've only listed all the coordinates where 1 is the first coordinate. So then maybe now list all the coordinates where 2 is the first coordinate. So 2 and 3, 2 and 4, 2 and 5, 2 and 6, 2 and 7, right? Okay. Now let's do all the coordinates where 3 is the first coordinate. So again, it's going to be 3, 3, 3, 4, 3, 5, 3, 6, 3, 7. And then now 4, right? So 4 and 3, 4 and 4, 4 and 5, 4 and 6, 4 and 7. So yeah, I believe I've listed every single item here, right? Because again, the first coordinate can only be one of these, and then the second coordinate can only be one of those, right? So why do they call it product? Well, this set has 4 elements, this set has 5 elements. How many elements did it end up creating in total? 1, 2, 3, 4, 5, another 5, another 5, another 5, 5 times 4. So then this set ended up having 20 elements, right? One interesting thing about this Cartesian product, that even though you might think it mimics multiplication, though, the set E cross F is not equal to the set F cross E. So what does it mean? Well, I had never even defined this. Let me do this definition. Two sets are equal. So a set A and a set B are equal if and only if A is a subset of B and B is a subset of A. Very important definition. So what am I saying? The only way two sets are equal is if they both contain the same elements. Well, how do you say that they both contain the same elements? Well, it's to say that every element here is also here, but at the same time, every element here is also there, right? That this is a subset of that, and at the same time, this is a subset of that. So when I'm saying that these two things are not equal, it's because they don't contain the same elements. Well, what can I say? So for example, see how every coordinate ends in 1, 2, 3, or 4, right? They start with either 1 or 2 or 3 or 4. Well, for example, we know that 5 is definitely not in E, right? So just to quickly show that these two sets are not equal, right? If the coordinate 5 comma whatever, 5 comma 3. This coordinate 5 comma 3 definitely is in F cross E, right? Because is it true that the first coordinate is from this set? Yeah, 5 is in F. Is it true that the second coordinate is in E? Yeah, 3 is in E. So the element 5 comma 3 is in FE. But this coordinate is not in E cross F, right? I just, I took the time to list out every single element in E cross F. Do you see 5 comma 3 anywhere? No, right? Because these coordinates all either start with 1 or with 2 or with 3 or with 4. So where's 5 comma 3? It's not going to be there, right? So I don't know. I think this is kind of interesting, right? That you might think, this is an axiom of real numbers. A times B equals B times A. And again, you might take it for granted. Oh yeah, for sure, multiplication. A times B equals B. But this kind of looks like multiplication, right? And yet, we got something that are not equal. E times F, if you want to think of it that way, is not equal to F times C, because again, they don't contain the same elements. Case in point, F times E contains 5 comma 3, but 5 comma 3 is not an element in E times F. So it's not true that they're both subsets of each other, right? This means that F cross E, again, maybe put it in parentheses. This shows that F cross E is not a subset of E cross F. the fact that it's not a subset is going to imply that they're not equal, because again, in order for two sets to be equal, they both have to be subsets of each other, and we just shown that this is not a subset of that. So see, sometimes you think things for granted. This means you might think that somehow this thing would imply that thing, but it doesn't. Okay, but yeah, this is the last thing I want to talk about, and I guess it is going to end up being 30 minutes. But why did I really want to talk about this set? It's because, again, right, it's coordinates. You've seen this before, maybe, again, if you've taken an algebra class, right? Because the xy plane, for example, right, where you draw all your pictures in algebra class, we see this is the x-axis and this is the y-axis. Well, this is a set. It's the set of real numbers cross real numbers, which sometimes we just call r squared. But yeah, this is the set of all coordinates a comma b, so long as they're both real numbers. A is a real number and b is a real number. So yeah, the two-dimensional plane, or the xy plane, is actually a set, right? And again, you cannot talk about functions or graphs without talking about this, right? So that's why I really wanted to make some time and introduce this new set, right? So a cross b is the set of all coordinates, where the first coordinate is in a, the second coordinate is in b. But it's also interesting to show that, yeah, it's also interesting to note that, yeah, this is a binary operation on the set. Anytime you have two sets, you can always create this whole new set called the Cartesian product, right? Nice. Okay, I just can't help myself. Well, okay, like I said that these two sets are not gonna be equal, right? Just because we can definitely see that this is not gonna be a subset of that, so that's gonna ruin everything, right? But and you can write out what f cross e, the same way that I wrote e cross f, made a list. You can write what f cross e is if you want to see every single element that's in this set, right? Well, I thought to myself, well, okay, so these sets are not equal. So if they're not equal here, they're probably not equal in a general sense, right? But one interesting thing that I noticed is that e cross f, right? This is a set. Suppose that I intersect this with f cross e. And what am I saying? I just want to see which coordinates they have in common, right? So notice that now I'm using a binary operation sets on two sets that I got from binary operations. So I'm making sets out of sets out of sets, Well, I noticed, I might be wrong, but I think the only elements here are 3, 3, 3, 4, 4, 3, and 4, 4. And if I'm wrong, please let me know, But this looks kind of interesting. Doesn't this look like E intersection F cross E intersection F, right? Because remember, E intersection F was just 3 and 4, right? So if the only elements here are 3 and 4, the elements here are 3 and 4, what are all the combinations of coordinates can I make? These 4 seem about it, right? So I wonder if in general A cross B intersection B cross A is this always gonna be equal to A intersection B cross A intersection B? Would that happen no matter what sets you have, right? So again, if this right here is true, well, this is just one example of it being true. One example isn't a proof, right? Or that being said, right? While one example is not a proof, one counterexample definitely proves that the statement is false. All you need to do to disprove something is to find a counterexample. So what maybe I'm thinking letting you guys try out is maybe create a bunch of sets AB, like AB is this thing, and then AB is something else, and then AB is something else, right? Try it out like if it's an actual science experiment, and try to see does this statement always hold, you know? So if you do it, if you try it with some sets and it continues to be true, then it might be true, right? But again, 4 examples, 5 examples still isn't a proof, right? So if you were to prove this, how do you think you would go about it, right? The only hint I can give is this, right? If you're saying that this set is equal to this set right here, all of that is equal to all of that. Well, like I said, there's only one way to prove two sets are equal. This is the golden standard. The only way you're gonna prove two sets are equal is to prove that they're subsets of each other. So suppose that you are convinced. Oh, I do think this is a true statement. How would you go about proving it? Well, this is the key. The only way you're gonna prove that this and this set are both equal is to prove that this is a subset of that and that this is a subset of that. So again, I'm not going to say if the statement is true or false. If you can find a counterexample, then that's all you need to say that the statement is false. But if you struggle to find a counterexample, try proving it, right? How would you and then that's my hint. How would you prove it? Try to see if you can prove that this is a subset of that and then prove that this is a subset of that. Well, let me know how it goes in the comments. Oh, by the way, I meant to show you this as well. Part of the reason why I introduced subsets in the first place. This is kind of interesting, and see if you can prove it or disprove this as well, right? Again, proof by picture isn't really a proof. But A intersection B. Well, okay. Let's suppose that you take the picture as inspiring, right? Well, if you remember the picture of the Venn diagram, it looks like A intersection B is a subset, again, by picture. A intersection B is a subset of both A and B, right? Similarly though, right, both A and B seem to be subsets of A union B, alright? So we have A intersection B, A, B, and then A union B. So this seems to be like the connection of the union and the intersection, right? That the intersection is a subset of both of them, whereas with the union, both of them are a subset of the union, and they form this little chain of subsets. Yeah, I wanted to mention that too. Make sure to like the video. So yeah, the last set we looked at, the Cartesian product, is what it's called. Right, did it look familiar, or did something about it look familiar? Well, yeah, right, coordinates. You've seen that when you graph an equation or a function. And that's why I wanted to talk about this before talking about functions. Well, don't forget to like, subscribe, and leave a comment. Let me know what you think about sets. Do you like them more now? Do you see that it was worth talking about them in the first video or not? Let me know. Alright, see you next time.